As everyone else gets in here, good morning. Welcome back. I hope your day went well yesterday. Before we get into our lesson for today, there's a couple of like housekeeping things I want to talk about. Obviously, next week, many of you will be returning to campus for the first time this year. And you'll be split into 2 cohorts. So you'll either come to school on Tuesday and Thursday, or you'll come to school on Wednesdays and Fridays. You'll attend the other day that you're not here virtually. And that'll be very similar to what you've been doing. It should indicate, or you should have been notified in some way, which cohort you are in. If you're in cohort A, I believe you attend on Tuesdays and Thursdays. And cohort B will be Wednesdays and Fridays. And then also some of you selected to remain virtual, in which case you'll continue attending as you have been by logging into Teams and doing that. Classes will still, have Teams running and all that stuff. So with that, some of you may or may not know where my classroom is. And since this is first period, this will be the first class you're supposed to go to on Tuesday or Wednesday morning. And then I think we'll have schedules to pass out to you guys so you know where all your other classes are and all that stuff. Because some teachers may have moved classrooms from previous years. So we want to make sure people know where to go. So with that, my classroom is in like the very back corner of campus. I'm in room 737. Some of you might know where that is. I'll type it in the chat here. Right. If you know where the print room is, like the print and graphics classroom, my classroom is just to the right of that. Also, if you know where Miss Young's classroom is with photography and yearbook and all that stuff, my classroom's back over there. You should be able to find it. I always have my door open. My name and room number on my door. I've got it printed out. Also, some of you, when you were freshmen, you may have had for Math 1, Miss Seitz. And I'm in her old classroom, so if you know it from there. So anyway, I want to make sure people know where my room is, because that might be important. It might not, you may not have seen what room I'm in anywhere on anything, or you may not have noticed it, so now we know. I'm in room 737. Basically just walk to the back corner of campus and you'll find it. I'm way back there. So there's that. Are there any questions about when you guys return to campus next week on Tuesday or Wednesday? Do you know what cohort you are in? Or does anyone not know what cohort they are in? Okay, well, I'll take the silence as saying that you know what cohort you're in, you understand what my classroom is, and you have no questions about next week so far. So awesome. If anything does come up, if you do have any questions, please feel free to ask, let me know. Happy to help. And so with that, we're going to start our lesson for today. The goal for today is to get through the lesson on section 10.2. Right, so essentially yesterday and today we're just doing notes. We're getting all the information we're going to need so that then we can practice with this stuff with section 10.1 and 10.2 about comparing two proportions and two means next week. All right. So we're going to get started with our presentation for section 10.2. So I do recommend that if you have something to take notes on, and that you are taking notes, please have that ready. And we are going to get started. All right, so here we go. We're doing the second section of chapter 10. There are only 2 sections in chapter 10, comparing 2 populations or groups, and section 10.2 is comparing 2 means. This will be very, very similar to what we saw yesterday with comparing 2 proportions. We'll deal with sampling distributions and confidence intervals and significance tests, dealing with means rather than proportions today, and all the accoutrements. Okay, so in this section, our goals will be to be able to describe the shape, center, and spread of the sampling distribution of the difference of 2 sample means. Right, and remember, sampling distribution that was introduced in chapter 7. Be able to determine whether the conditions are met for doing inference about mu1 minus mu2. And again, those conditions are the things that we've checked in chapter 7, 8, and 9, having to do with being a random, our 10% condition, and our large counts conditions. I'm sorry, not large counts. Normal/large sample condition for means. I apologize. Construct and interpret a confidence interval to compare 2 means. That is chapter 8. Perform a significance test to compare 2 means. Chapter 9. And determine when it is appropriate to use 2 sample T procedures versus paired T procedures. And so this will hopefully give us some idea of when to use the correct strategy, right? Because we saw the paired T procedures at the end of section 9.3, right? But now we will also have our 2 sample T procedures. Those are the goals. So what if we want to compare the mean of some quantitative variable for the individuals in population 1 and population 2? So again, we're dealing with 2 separate populations. Our parameters of interest are the population means mu1 and mu2. The best approach is to take separate random samples from each population and to compare the sample means. Suppose we want to compare the average effectiveness of 2 treatments in a completely randomized experiment. We use the mean response in the 2 groups to make the comparison. So again, just like we saw with our proportions yesterday, we can do a 2 sample kind of like procedure with means, dealing with 2 populations in a mean about of characteristic within a population, or we can use it to compare results in an experiment. Okay. So we have our 2 different kind of scenarios. And then again, we get very similar kind of notation ideas for our 2 samples. We get our population or treatment 1, parameter is mu sub 1, the statistic is x bar sub 1, the sample size would be n sub 1. And similar for population or treatment 2, we get mu sub 2, x bar sub 2, n sub 2. And again, that allows us to identify which parameter, statistic, and sample size goes with which population. We can use other things if we want instead of numbers 1 and 2. Like if we're comparing children and adults, we can use the subscript C and subscript A to identify which parameter, statistic, and sample size goes with each population. Okay, so we can use letters in the subscript as well. We don't always have to use the numbers 1 and 2. I say that because you might see examples that use letters as subscript. To explore the sampling distribution of the difference between 2 means, let's start with 2 normally distributed populations having known means and standard deviations. Based on information from the U.S. National Health and Nutrition Examination Survey, the heights in inches of 10-year-old girls follow a normal distribution, N 56.4, 2.7. Remember, this notation All right, the first number here is the mean, and the second number is the standard deviation, and it is normally distributed. The heights in inches of 10-year-old boys follow a normal distribution, N 55.7, 3.8. Suppose we take independent SRSs of 12 girls and 8 boys of this age and measure their heights. Again, notice our sample sizes in this case don't need to be the same. What can we say about the difference X bar sub F, right, female, minus X bar sub M, males, in the average heights of the sample of girls and the sample of boys? So again, they're choosing to use F and M instead of 1 and 2. Still works out the same. All right, so using Fathom software, we generated an SRS of 12 girls and a separate SRS of 8 boys and calculated the sample mean heights. The difference in sample means was then calculated and plotted. We repeated this process 1,000 times. The results are below. All right, so we have the sampling distribution for the average height of the females in our samples, sampling distribution for the average height of the males in our samples, and the sampling distribution of the difference between their heights, females minus males. All right, and again, they chose the order they did, female minus male, because based on our normal distribution numbers, the girls are typically a little bit taller than the boys, and we end up with more positive numbers than negative numbers, which positive is easier to work with. And so we see that all these distributions are approximately normal, right? Our mean, 56.4, 55.73, 0.8 for the standard deviation, 1.35 for standard deviation here. Right, and then we get the approximately normal distribution for the difference. The mean is 0.67, the standard deviation is 1.56. All right, and so what do we notice about the shape, center, and spread? Well, we just kind of talked about that in the sampling distribution. All right, and we'll get more into those specifics, but just as a preliminary evaluation of this, we could see that we ended up with a mean that is positive over here, meaning that on average, 10-year-old girls are taller than 10-year-old boys based on this data. Okay. Is there anything I can clarify so far? So both X bar 1 and X bar 2 are random variables. The statistic X bar 1 minus X bar 2 is the difference of these two random variables. In chapter 6, we learned that for any two independent random variables, X and Y, these are the same results that we used yesterday. Mu, except now we're dealing with mu instead of P. Mu X minus Y equals mu X minus mu Y. And the variance of X minus Y is equal to the variance of X plus the variance of Y. So we then get some definitions and ideas for the sampling distribution of the difference between two samples. All right, so we can choose an SRS of size N1 from population 1 with mean mu1 and standard deviation sigma 1, and an independent SRS of size N2 from population 2 with mean mu sub 2 and standard deviation sigma 2. Right. Our shape can be determined when the population distributions are normal. So if we know that both population distributions are normal, sampling distribution of X bar 1 minus X bar 2 is approximately normal. In other cases, the sampling distribution will be approximately normal if the sample sizes are large enough. Right. N1 is greater than or equal to 30 and N2 is greater than or equal to 30. Right, this is our central limit theorem idea from chapter 7. Okay, these are the same conditions that applied to a single population from chapter 7. We're now just applying it to the difference. So if we have two populations and both populations are approximately normal, then the difference of those sampling distributions will be approximately normal. Otherwise, if the sampling distributions are both large enough, greater than or equal to 30, we'll also have an approximately normal sampling distribution. Center, the mean of the sampling distribution is mu1 minus mu2. And that, again, is carried from chapter 6 with our random variables. And then the spread, the standard deviation of the sampling distribution of x1 minus x2 is the square root of the variance of population 1 divided by n1 plus the variance of population 2 divided by n2. As long as each sample is no more than 10% of its population, 10% condition. So again, within these things here, we have our 10% condition in order to find the standard deviation. And we have our central limit theorem that applies to the shape when the population distributions are not normal. So we have our conditions here. Do you need a moment to write anything down from this screen? And again, we have our visual here. We have the curve that represents the sampling distribution of the difference of the sample means. Right? The horizontal axis represents all possible values of the difference of the sample means. We have our standard deviation represented by the square root of the variances divided by the sample sizes, and the mean is the center. So that's our sampling distributions, and now we're going to look at the two-sample t-statistic, which comes up in confidence intervals and significance tests. So when data come from two random samples or two groups in a randomized experiment, the statistic x bar 1 minus x bar 2 is our best guess for the value of mu1 minus mu2. When the 10% condition is met, the standard deviation of the sampling distribution of x1 minus x2 is sigma, difference of the means, equals the square root of the thing we just saw previously. The variance of population 1 divided by the sample size, and the variance of population 2 divided by its sample size from our sample. If the normal condition is met, we standardize the observed difference to obtain a t-statistic that tells us how far the observed difference is from its mean in standard deviation units. You remember t-statistic goes along with table B. Since we don't know the values of the parameters sigma 1 and sigma 2, we replace them in the standard deviation formula with the sample standard deviations. The result is the standard error of the statistic x bar 1 minus x bar 2. So we get standard error of the difference of the sample means is equal to the square root of the standard deviation of the sample, or the variance of the sample divided by n1, plus the variance of sample 2 divided by sample size of sample 2. Right, so we replace sigma with our sample standard deviations in our formula here, we get the standard error. And this gets us to how we calculate our t-statistic, which is used in both confidence intervals and significance tests. All right, so we have t equals the difference of our sample means, x bar 1 minus x bar 2, minus the difference of the population means, mu1 minus mu2, divided by the standard error. The two-sample t-statistic has approximately a t-distribution. We can use technology to determine degrees of freedom, or we can use a conservative approach using the smaller n1 minus 1 and n2 minus 2 for the degrees of freedom. Okay. And so then we get our conditions for performing inference about mu1 minus mu2. We have random. The data come from 2 independent random samples or from 2 groups in a randomized experiment. 10% when sampling without replacement. Check that N1 is less than or equal to 1/10 of capital N1, right? Less than 10% of the population, and that N2 is less than or equal to 10% of the population of population 2. And then our normal large sample condition, both population distributions or the true distributions of responses to the 2 treatments are normal, or both sample sizes are large, N1 is greater than or equal to 30 and N2 is greater than or equal to 30. If either population or treatment distribution has unknown shape and the corresponding sample size is less than 30, use a graph of the sample data to assess the normality of the population or treatment distribution. Do not use 2 sample t procedures if the graph shows strong skewness or outliers. So it's the same 3 conditions that we did with confidence intervals and significance tests, with the added thing that we need to check these things for both populations and samples. Okay. Does anyone need a moment to write anything down from this screen or from the previous screen? I kind of jumped on to the next one really quick. So this leads us to our confidence intervals for mu1 minus mu2. The 2 sample t interval for a difference between 2 means. This would be our inference method to determine a confidence interval. When the conditions are met, an approximate C% confidence interval for mu1 minus mu2 is the x bar 1 minus x bar 2, the difference between the sample means, plus or minus t star, the t statistic, times the standard error, square root of the standard deviation of sample 1 divided by the sample size from sample 1 from population 1 plus the standard deviation of sample 2 divided by the sample from population 2 sample size, where t star is the critical value with C% of its area between negative t star and t star for the t distribution with degrees of freedom from either technology or smaller, or the smaller of N1 minus 1 and N2 minus 2. So again, this right here is saying I'm going to use the smaller degree of freedom. Right, so if I'm sampling from the 2 different populations and one of my sample size for N1 is 30, my sample size for N2 is 40, right? I'll have degrees of freedom of 29 and 39. I will use 29 for the degrees of freedom rather than 39. Okay, because it is the smaller degree of freedom, is more conservative. All right, and that goes along if you're using table B. If we're using technology, which there is ways to do this on the calculator, I have the videos in our resources and we'll see them used next week. We can use technology. So we need a moment to write any of this down for their notes. And then we get to significance tests for mu1 minus mu2. An observed difference between 2 sample means can reflect an actual difference in the parameters, or it may just be due to chance variation in random sampling or random assignment. Significance test helps us decide which explanation makes more sense. The null hypothesis has the general form H sub 0 such that mu1 minus mu2 equals the hypothesized value. We're often interested in situations in which the hypothesized difference is 0. The null hypothesis says that there is no difference between the 2 parameters. So we can write it as H sub 0 or H naught such that mu1 minus mu2 equals 0, or H naught such that mu1 equals mu2, representing no difference. The alternative hypothesis says what kind of difference we expect. Either the difference will be greater than 0, the difference will be less than 0, or that the difference is just not 0, could be greater than or less than. And in this case, this alternative leads us to a two-sided test. All right. So again, this is following a lot of the same ideas and rules that we've seen in previous chapters. See, we need a moment to write anything down. To do a test, we need to standardize x bar 1 minus x bar 2 to get a two-sample t statistic. All right, and our test statistic equals statistic minus parameter divided by the standard deviation of the statistic. And we get t equals x bar 1 minus x bar 2 minus mu1 minus mu2 divided by the square root of standard deviation of sample 1 divided by, or the variance of sample 1 divided by the sample size 1, variance of sample 2 divided by the size of sample 2. That is our t statistic. It's the same t statistic we just saw represented earlier. Find the p-value. Use the t distribution with degrees of freedom given by technology or by whichever one's smaller again. Degrees of freedom equals smaller of n1 minus 1 and n2 minus 1. So again, just like last time, we're going to err on being more conservative and use the smaller degree of freedom between the two sample sizes. And in this case, the mu1 and mu2, those will be the hypothesized values, right? Which, if we're saying that they're the same, this value is 0 most of the time. And we get our inference method here, the two-sample t-test for the difference between two means. Suppose the conditions are met to test the hypothesis, h naught such that mu1 minus mu2 equals the hypothesized value. Compute the t statistic. And that's the t statistic we just saw here. T equals x bar 1 minus x bar 2 minus mu1 minus mu2 divided by the square root of s2 sub 1 divided by n1 plus s2 sub 2 divided by n2. We find the p-value by calculating the probability of getting a t statistic this large or larger in the direction specified by the alternative hypothesis h sub a. Use the t distribution with degrees of freedom approximated by technology or the smaller of n1 minus 1 and n2 minus 2. And just like from chapter 9, right, if we're looking at the alternative being that we are greater than the hypothesized value, we find the t-value in the proportion under the curve greater than that. If we're doing less than, we find our t-value and go to the proportion under the curve less than that. And if we are two-sided, we find one of the t-values and find the proportion greater than it or less than that, and we double it. Multiply it by 2. All right. So, could you please raise your hand if you need a moment to write any of this down for your notes? And lastly, we have using our two-sample t procedures wisely. In planning a two-sample study, choose equal sample sizes if you can. This is referring to if you're doing in a study, so like an experiment. So if our sample sizes can be the same, it works out better. It's more reliable. That's if you are planning a study. If you're giving a problem to solve and they tell you the size of the samples in your study, you really have no control over that. But if you're asked to design a study, you want to make sure to choose equal sample sizes if you can. There's a thing called a pooled two-sample t procedure. We will not get into that in this class, and we will not use it. So if you see it, don't use it. We are safe using 2 sample T procedures for comparing 2 means in a randomized experiment. Do not use 2 sample T procedures on paired data. So again, I think the major difference between paired data and essentially like 2 sample data, right? The 2 sample procedure is used when you're comparing 2 populations or 2 means in an experiment, right? From like 2 different treatments, so to say. You will use paired data if you have from a single population 2 things to compare. So even if you're doing an experiment and you take one person, like we saw the experiment yesterday in section 9.3, where one person gets 2 different treatments on different days, and we're comparing means of some result that we're measuring, that would be paired data, right? So we want to try to make that differentiation. Are we looking at paired data, or are we looking at data coming from 2 different populations or 2 different treatments with 2 different sets of people? Okay. Beware of making inferences in the absence of randomization. The results may not be generalized to the larger population of interest. All right, so this is more again referring to experiments where, like, suppose you're doing an experiment, but the people that are participating were not randomly selected, but it's what you have to work with, right? They're volunteers. You can only make inferences about the people and people similar to those types of people in your experiment. Okay, you cannot necessarily make inference about the general population or the larger population you're interested in. It can only apply to the types of people that participated in the experiment. So you have to be careful on how you state your results in your conclusion. Okay, is there anything I can clarify? And that gets us to the end of the notes. All right, so we went over each of these things. It was rather brief. We did not see examples really yet. We will next week. I'll make sure to do examples and let you guys practice and do all of that next week. And hopefully that'll help it make more sense. But this is all the notes. This is all the stuff we're going to be using. So, there it is. And that. And that. All right. So, does anyone have any questions, comments, or concerns before we end the class? Anything at all about the lesson, about returning to campus, about previous assignments, anything, any questions? I know today's class was kind of short and fast and sweet, so hopefully that gives you time to go have some breakfast or relax and, you know, slowly prepare for your next class. If you guys do have anything else that comes up, any questions about the class, any questions about returning to campus, anything at all, please feel free to let me know. I'm happy to help. But that is it. Have a great rest of your week. Have an awesome weekend, and I'll see you guys, most of you guys, hopefully live in person next week.